Hello everyone. This is week number 4, and we've been talking about formally describing structures. First, we needed to be specific about how to build problem instances in the first place, and for interesting problems that sort of space, data space is essentially too large, arbitrarily large, essentially. And the way we capture this is relying on the notion of countable infinity. Because for finite problems, you don't need a theory. You can just list all the instances of the problem and be done with it. At least that's what I used to think. But if you think about some finite and incredibly large problems, actually you need an algorithm. For instance, if the universe is finite, then your theory of physics cannot be simply just number of particles in the universe, because your theory is as big as your data, and that doesn't really sound like a theory. So it's not just countable infinity that we're getting at. We're saying, well, there is some structure in it that you don't have to enumerate through finite instances. You just capture something in it inherent, and instead of going from one instance to the other without understanding what's in these instances, you can write a theory in the form of a grammar description or an automata, and just gives you the summary of what's the basic understanding of the structure in it. Okay, so even for potentially finite but arbitrarily large problems, you're going to need a theory. Okay. So if you believe language is countably infinite, which was essentially from Humboldt's idea, but the creativity in languages arises from this potential infinity. Yes, but it's potential. Essentially, the whole point is that even if you have a finite solution to the problem, that's going to be in the form of a grammar rather than the instances of the solutions themselves. You're going to say, this is my understanding, even though the problem is finite. Okay? So for arbitrarily large problems, whether they are finite or infinite, you need to be able to represent the problem and go from one instance to the other. And if you want to understand what allows you to go from one instance to the other, you're going to need a theory, and that's what the formal structures are for. Okay, so that's what we're getting at. At this point, I give you hierarchical organization in the form of context-free grammars. And I give you some examples. Let me give you more examples to give you an appreciation of why we write grammars in the first place. And then you're going to get more appreciation of when you see how these grammars can be turned into algorithms in the form of an automaton. So take this example that I've been calling mini English. Right? It has structure in it because if you can turn English words into formal objects, it's the vocabulary is I, like, you, and think. Just 4 formal symbols. I'm not calling it words anymore because I'm going to write a formal grammar for it. Just 4 symbols in my alphabet as the building blocks. And the language I told you was like, I like you is in mini English. I think I like you is in English. And interestingly enough, you think I like you in English. So number of words are the same, but the meanings are not. So you need to be able to say, well, what's going on here? How can I distinguish these two? Because they don't mean the same thing. That's the sort of some pointers for things to come in the course. I'm capturing something, but not everything in the order of 3 is three symbols in it is in this mini English. For instance, this is maybe Tarzan English, but not mini English. Also, so example of lang 3, and it's not grammatical, so you can't simply say, well, give me all words of, all sentences of lang 3, they'll be in mini English. Well, this one is not. How do you distinguish? Okay. Slightly more interesting example. I think you let's assume this is not in mini English. And this is a more interesting problem than I like you versus like you I, because there is something in it that looks pretty much like this one. I just replace think with like, and I'm out of the language. So that's what I'm getting at. Like when you see things with similar metrics, number of words, number of symbols, whatever, and when you realize that none of these metric properties are decisive in keeping it in the language, then you're going to look for structural cues to distinguish these things. And one way to do this is to write a grammar. Here's first attempt. In my context-free grammar notation, in other words, mini English as a formal grammar, I can say, well, here's a bit of linguistic terminology. Well, in this language, there seems to be noun phrases, so my variables are now sort of meaningful in some sense. It's a noun phrase followed by a verb phrase, so MPs. So I'm now writing a more empirically motivated but formal grammar. And I can say, well, these noun phrases can be proper nouns, like I or you. Okay. And these verb phrases are things that are headed by verbs. And in the case of things like, they take a noun phrase, the likey. In the case of verbs like think, they take a clause. I think a clause. So it's got a verb followed by another S. Okay. And the verb could be like or think. And of course, S goes back to that. And this is a first attempt in understanding mini English. And we can use this to say, well, is I like you in the language? But remember the definition of being in the language of a grammar. If this is the grammar, being in the language of this grammar means give me a string. If I'm able to drive it, I'm able to connect it to S, it is in the language. Well, there's only one way to write S, so it's going to be MP, VP. And now I have two symbols, and at this point, for which one I use a rule, I'm not giving you an algorithm. I'm going to talk about that starting next week. Let's pick this one. Let's rewrite this one. There's a rule for I, so it's going to be I, VP. And then now, this is a terminal. It's in my vocabulary, but this is a variable in my grammar. And this variable can be written like VMP. This is a terminal, these are not. So let's pick this one. And now these two are terminals, this one is not. And fit in. So I'm able to go from S to I like you, and this is fine. This means this is in the language of my grammar. And if you try and derive you like I, it'll be fine, right? So I'm not saying mini English is properly, this is the proper description of mini English. I'm just saying it gives you some structure because at least it's going to eliminate this. Right? Like UI is not derivable by this grammar. Why? Because I cannot start with S do MP VP and be able to put like in place of. Remember, this is when you write things like this, remember this is a string. It's just that it happens to have unknowns in it. Once you replace them with knowns, like terminals, they're going to be in order. So if this MP could lead to like, maybe the rest could lead to UI, but this cannot lead to like. Therefore, you're stuck, according to this grammar. Okay. And you can say, all right, so this grammar captures some structure in mini English. But when you look at this problem, let's try, I think I like you. First, I'm going to show you the rule use, and then I'm going to show you how you can represent that as a tree, because essentially the trees that you draw are arising from uses of rules. So I can start with this. Well, it says only I can only write MPVP. This could be I, and this could be V followed by S. V could be think, and S can only be MPVP, so I think MPVP. And this could be I. And then if you go, okay. VP can be I think I V MP, and this V can be like, and this MP can be U, no more variables left. I started S, so I think I like you is in the language of this grammar. And you can draw this rule use as a tree. So it's going to be 3 headed by this, and it's going to be, at every step, I just notate the rule used. I use this rule. Here I use this rule, and V goes to I. And then for VP, I use VS. And then for V, I used think. And then for S, I used MPVP. For MP, I used I. For VP, I used VMP. And for V, I used like. And for MP, I used U. Okay. So the way you can see this tree corresponding to this is that when you look at the leaves of the tree, they're all terminals. So this is graphical description of rule use, essentially. Okay. So when we talk about automata, we're going to see that whether we do this from top to bottom or bottom to top is the way you turn it into an algorithm. At this point, this is just grammatical description turned into a tree. It doesn't tell you how we can combine sub-pieces of the tree to make larger pieces. Okay, that's automata. That's an algorithm. Grammars don't compute. Grammars describe. Okay, but there is a very direct way to turn grammars into computational devices, and that's one of the major points of the course. Now, this is fine, but there's something missing about grammar than just simple Tarzan mini English. Like you, of course, you want to eliminate that. But why is it not eliminating this? I like, I think you. And I said, let's assume this is ungrammatical. So it's not me. I like, I think you. That's not what this is not what is meant by this sentence. Let's assume that. If I'm going to leave it out, at this point I can't, because I can't draw a tree for this, right? Going to be and this is going to be, I think, you. And here's another convention. You draw a triangle if you're not interested in the internal structure anymore. And you know how it's going to expand to you. The critical point here is, well, like, we take it as a formal object, but in real life, like is as a predicate is a bit unlike think. Think takes clausal complements. It takes a proposition. I think something. Like takes a noun phrase. Like takes a term. You can talk about action. I like fishing for in the Sea and things like this, but that's different. That fishing, that the ing makes it a little bit different. So if you want to be able to distinguish between like and think, is there anything you can do in grammar to do that, or do we just leave it to nature to say, please distinguish think and like for me? Well, you can do that, but you can also help nature by being more specific about what kind of structures you want to arise from your grammar. So you can, let me just rewrite, I like my mini English. So this is second grammar. And the reason why I'm revising my grammar is now I want to turn my formal description of English into something closer to English. And so because I'm going to build models of it in the end, I'm not just interested in formal objects. I can say, well, yes, clauses consist of subjects and predicates. That's what Aristotle called them. This will be subject, this will be a predicate for Aristotle, but nowadays, formally speaking, we call it noun phrase, verb phrase. In fact, we call them thema and rima, but we'll talk about this later. You can say, all right, noun phrases, I'll just leave you as is. In other words, Although I like you is fine, you like I is a bit odd, but I'm not trying to solve that problem. I'm going to do that later. I want to be able to distinguish between like and thing kinds of predication. You can say, well, verb phrases are verb phrases. It's just that if you're going to have a noun phrase, you better have, let's say, a transitive verb. And if you're going to have a sentence, and that sentence, a subclause, is meant to be an argument of this verb better be taking a complement clause. And then you say, well, you know, like is VT, whereas think is VComp. And this you can think of this as a feature of this variable. Or you can just combine them and make them atomic. Okay? But essentially, I'm trying to make this formal grammar more empirically closer to what we know as English. Okay? Step by step. I'm not taking care of this. In other words, I'm not taking care of case marking because it doesn't say anything here that this can only be nominative in English, because the accusative of I is me. Okay, I'm not taking care of that. I'm just taking care of like versus think. So if you think of it that way, then I like, I think you is going to fail at this point. If you say, okay, and PVP, I, because I have like, I have to have this, and this is like. It's just that this cannot be I think you. In other words, you cannot make this noun phrase, if you, according to this grammar, you cannot make I think you a noun phrase to be for it to be interpreted as a term rather than a clause. Okay? Why? Because now you're using this rule, and you can use this rule for like, because like is only VT, it's not VComp. Incidentally, this also eliminates I think you, but if you want to say that in English, you can say I think of you. But I think you, I mean, it's essentially eliminated by this as well. Why? Because I think will take complement, and you is not a complement, so it's going to take, it needs going noun phrase, but think is not considered to be transitive. Okay? And you can do this for any organized behavior, if you think about it. But right now, I'm trying to give you some formal examples. I'll give you some examples from planning and vision later on. But at this point, you begin to understand how some subtle constraints in the data can be captured formally without just being able to talk about it all the time. Or think and like are different things. Well, what is it? How do you show the difference is the critical question in cognitive science, right? Because unless you address the how question, you cannot model it. And without modeling it, we don't really see the limits of behavior. So good models are faithful reflections of a good theory. That's the whole point. So I'm going to talk about this as we proceed. Okay, so that's the way we sort of revise our assumptions about grammar description, the internal structure in the grammar, in the language, so that when I begin to compute, everything is transparent. I don't have to worry about these anymore because I've captured the intrinsic constraints in the grammar in the first place. Computation just does what my grammar tells me. Okay, that's the whole point. So let me give you some formal examples. I mean, it's not only in this kind of language domains that you're worried about structure. Just think about arithmetic. Just 4 operations, right? I mean, if I give you this, if I give you that's more interesting, something like this, you have a certain interpretation of this with your understanding of arithmetic, that something has priority over these things, so you do that, and then or if I want something else to be meant by it, I can say, well, take these three and then multiply by 2 and take a difference. In other words, the way you structure these operators has a significance in the value. I mean, you're going to get different values depending on in what order you do the operations. So how can we do this? Well, if you're only interested in val formness, let me call this grammar 1. And here I'm only interested in val formness of arithmetic expressions. In other words, that's a val formed expression. This one is not. 5 plus 3, 2 times. This is not arithmetic. Okay? So if you want to just distinguish these two, you can say, well, start, have plus or minus or times or divide or just let's say the simple numbers 1, 9, or just parenthesize. Now if you do this, if this is your grammar, 1, 2, 3, 4, 5, well, 10 rules and one more, 16 rules. Okay. So what is the building blocks? Well, 0, 1, 2, 9, followed by left parentheses, right parentheses is my vocabulary. And plus the operators, of course, minus, division, and times. So these are the building blocks of arithmetic, and this shows you what kind of arithmetic expressions are well formed. If this is all you care about, it's fine. This is a formal language, and this is a formal grammar, and because it eliminates that, how does it eliminate that? It's to get this, it's going to go like this. And then for that, it's going to be S plus S, and for that, it's going to be 5 plus S, 5 plus 3, then what? There is no way you can continue to come to this expression. In other words, you cannot start with S and come to this expression. But you can start with S and come to that expression. I leave that to you as an exercise. So this captures well-formedness, but I mean, you can deeply feel there's something missing here. You could do more, right? You could say, well, not only I capture well-formedness of an arithmetic expression, I can also capture the priority of these things as I do it. Okay? Because multiplication is has more priority or precedence than addition if it's not parenthesized. So what am I going to do? Am I going to list all these exceptions? Well, that's one option, but that's not going to give you an understanding of the problem. But you can restructure your grammar and see if it does what you intend to do. In other words, capture well-formedness and priority of the structures. So this is where you begin to put some meaning into structure, and we're going to do more and more of that as we proceed, once we take care of this formal landscape of what is possible with these tools. So the way I would revise this grammar is, well, okay, I know that plus and minus are at the same priority level. That's the way we conventionalize that arithmetic. Okay, I can say, all right, I'm going to use, rather than using one variable, I'm going to use more than one. If it is plus, I just do this. If it is minus, I do that. If it is something else, let's worry about that something else. And here, you say, well, if you have times, I have this. And again, look, it's not t times t. Why? We'll see soon. T divided by f. So I get these. So these are at the same level because they are in the same priority. These are at the same level because they have the same priority. This is division. But something has the highest priority, namely parenthesization and the numbers themselves. So this will be f, and f could be like 0, 9, followed by parentheses. Right? So why are we doing this? Just keep this. I'm just going to keep these two grammars on the board. This is G2, which is well-formedness and priority altogether. Instead of just saying, well, these are independent descriptions, but they don't. They are structurally related, okay? And you want to be able to capture that in one grammar. That's what we're trying to get at. Now this is G1. If you do G1, you can do this. But you could also do this. Which one is the arithmetic that you have in mind? Well, probably this one. But this grammar gives you both interpretations. When you look at this grammar, it's going to give you only that interpretation. Why? Because it's going to, at the top level, there is no multiplication. If it has to go to the term to be able to multiply. Okay? So it has to be and you might be thinking, well, if the only term is multiplication. If the only term is multiplication, you're going to skip all this, do the term, and do this multiply. So there's no problem. it's going to be interpreted like this, and this will go to T, T will go to F, and this will go to 3. This is another way of saying this has the highest priority because it forced me to go all the way down to highest priority level. And this is going to be T times F, and this will be F followed by 5. This will be 2. The trees are similar, but differing on the leaves. But the point is, there is no way for this expression. Just imagine doing multiplication on top using this grammar. If you want to do multiplication first, I mean, if you want to do this first and then you multiply, it has to look like this. And this has to go to 3 plus 5. And this has to go to 2. Right? Just like the other grammar. But the problem here is this. T is not going to give you that. T can give you multiplication, division, or highest precedence. So if you parenthesize this, it will be fine. But since you didn't, you cannot go back to S to get the plus. So this very, formal, uninteresting grammar begins to capture something very meaningful, that in our arithmetic things have priorities. And instead of just enumerating this all the time, you talk about arithmetic, you can build it into your grammar. Therefore, your computation will be very transparent because it has nothing to worry about. It doesn't have to say, so how did you do plus? Was it before or after multiplication? It doesn't have to worry about this because the grammar itself will give you the computation to be done transparently. Okay? So this will be the question part, and you won't be able to get it. So that's the thing that we're getting at when we say, well, these structures, we try and capture them because there's a meaning in that structure. I'm going to do something about that meaning. Okay? Let me give you some more formal examples so that we get to, familiarize ourselves with this formal notation. Here's another language. Let's say my vocabulary is just 0, 1, and my language is all and only strings in sigma star that starts with 0 and ends with 1. And you can sort of feel that this is a simpler problem. But it's not simple in the sense that the number of solutions are finite. There are infinitely many strings, countably infinite many strings, that satisfy this property. Right? So this is in the language. This is not in the language. This is in the language, and many other things are in the language. Okay? And as it turns out, there are many different ways you can study these properties. So in other words, there are many grammars that you can write for this, and only for very simple languages, like regular languages, you can actually prove that all these grammars do the same thing. If the problem is complex enough, you're not able to do that. But if the problem is simple enough, then you can write a grammar and show that all these grammars lead to a unique machine. Okay? But let's just write one grammar. And the simplest way, and the one I would recommend, is instead of thinking about this problem as you go, you can say, well, just do a divide and conquer. And say, we can say, well, just divide it into 2 because I have 2 properties. Make sure that A starts with 0 and make sure that B ends with 1. Okay, that's a simple way to do it. So how do I do that? A starts with 0. I can do that. And then if I have a 0, I can have anything. How do I write anything? Let's just write another symbol, C. C will be anything. So anything in this domain will be 0C or 1C or nothing. And B will be things that end with 1. Get something, just end with 1. Okay. So let's see what this grammar does. So like this is a divide and conquer strategy. I divide the properties into 2. A, get me things starting with 0 and followed by things. B, get me things, it's just that please end with 1. This is the simplest way to sort of conceptualize these very formal problems. So 0, 1 is in the language, and how do I get that? According to my rules. Maybe A goes to 0C, C can go to empty, and B can be 1. Started with S, ended with 0, 1, it's fine. So, for instance, if you notice, if you want to take 1 from C, let's say alternative root, AB, 0CB, and then say, let me just use C for 1 because I have this, 0, 1C, B, and then you say, well, now take C to empty, but now you're stuck, okay, because B cannot be empty, according to this grammar. So the way I organize my grammar, I have to take this root. So the critical definition of language, remember that being in the definition of a grammar, is if there is a path from S to the string, it's in the language. It doesn't mean all paths that you can follow must lead to something. Okay? Of course, if they lead to something, in other words, if they lead to something with no non-terminals, it is going to be in the language. But if you're stuck with this, you cannot say this is not in the language, because you weren't able to go all the way to make that decision. If you're able to go all the way in one path of use, then it is in the language. Okay. Take another one. 0011. Now you're going to see options, and that's the maybe I should leave that as an exercise. How can you do it? You can take care of this by A, you can take care of this by B. That's one option. Just try this out. Or you can take this by A, you can take this by B, because B allows that. So try it out. Just nice exercise. What else can you do? Well, you could take this by A and this by B, because it's allowed. There are at least 3 ways you're able to derive this one. Okay. And that's the problem with descriptions. Although they seem to be capturing a very simple conceptual property very rigorously, if you think of them as algorithms, they're not really algorithms at all. They don't give you, please follow this path. Okay? Algorithms, when you turn the grammar into a PDA, you're going to see that we can actually tackle this problem in a more flesh and blood kind of way. Okay. So let's do one more example. Well, maybe 2 more. This time, let's say AB and L2 is no B for Now, this is meant to be a very formal description of a language. I'm leaving it deliberately ambiguous and underspecified, not ambiguous. What this means is I want all and only the strings in which there is no B is followed by A. Okay? Even if I write something like this, what I mean is out of sigma star, give me all and only the strings in which no B is followed by A. But we have a tendency to write them formula like this, because implicitly our understanding a problem is, well, you must write the grammar such that you're addressing the problem rather than just, diverting the issue. Okay? So what is this language? Well, it can have many A's. It's just that the moment you have B's, you're going to have B's and nothing else. Okay? In other words, you cannot write something like this. Because they can mix A and B's in any order. And then you say, I go to A and just take B's. If you do that, you will be able to recognize A's and B's in mixed order. So you don't want to do this. Again, just do a divide and conquer, AB. Okay. So B is going to say, once you have B, be careful, state. So A can be, well, as long as you don't have a B, just keep going. That's this state. And of course, you can have nothing before B. The moment you have B, which is the end of start rule, all you have is B or A. And the reason I wrote it this way is this in the language is the critical question. There is no B, therefore no B is followed by A. So this is in the language. So you must be able to recognize it. How do you recognize it? Okay. It's just that after A you have to have B, and B can only be small b. Now, of course, if all problems were that simple, you wouldn't really worry about context-free grammars too much. But there are some interesting context-free grammars which are not regular grammars, regular languages themselves. So you're going to write some rules that really show you the true nature of context-freeness. Just think of this example. Again, just A, B. In these examples, I only give like two. In fact, the size of the vocabulary is not the source of the structural complexity. I'll show you. Right? In other words, just take this. A building block just one symbol. I mean, you can say, well, how can you possibly construct a complex structure out of this? Well, think of this language. Number of A's is such that I is a prime number. This is not a context-free language. There is no way you can write a hierarchical grammar for that. Okay? And the reason is as prime numbers get larger and larger, the next thing that you're supposed to do will be indefinitely apart from the previous instance. And even if you use recursion in grammar, you won't be able to do that because recursion allows you to give go step by step. So you won't be able to write a context-free grammar for this language. So it's not the size of the vocabulary that's the matter. It's kind of dependencies that you have in the language that makes a difference. So let's go back to AB again. And let's say my language, let's say L4, is such that not only I have A's followed by B's, just like previous example, I want number of A's and B's to be the same. That's what N stands for. That's when things begin to get structurally very demanding. Okay, so according to this, AB is in the language. ABB is not in the language. BA obviously not in the language because of order violation. But ABBB is in the language and things like that. Okay. So how do you do that? Well, one simple way is to write a grammar that looks seemingly simple, but it's actually doing something very profound. If you look at this grammar, the way it expands the trees will tell you why it's quite an illuminating capture of A and Bn. This could be ASP, ASP all the time until you stop the recursion. So this structure will always put one A at the left edge and one B on the right edge. So when you read this structure, there will be same number of A's going same number of B's. Okay. So having S in the middle makes a huge difference. Okay. Because if you write SASB, you'll be out of language because you can put AB, AB, and it says you can't do that. This is not a good solution. So once you get this idea, you might think, well, okay, so if you give the same number of things and if you extend these things, I should be able to do that. And that's when context freeness begins to break down. Just take a look at this problem. L5. And let's say it's AN, BN, CN. So if you're thinking, well, if you give me two things and you ask for the same number, I'll do that like this. Give me three, I'll do this, and it'll be fine. But you won't be able to write a context-free grammar for that. Because if you do this, if your idea is, let me get my A's in the beginning, I'll do my B's here. The moment you stop this and go to B, there is no way you can control that the number of B's that you use is the same as number of rule use. Okay? In context-free grammars, there is no control over the number of rule use. That's the reason for that is there's only one thing on the left-hand side. So they are context-free in the sense that all these symbols are used context-freely without having to worry about what you've done before. But there's a limit to what you can do with that. And this is not a context-free language. Okay? So that gives you an idea about rule use under these circumstances. Rule use means context-free rule use. In other words, you use the rule, and when you use the rule, you're not worried about number of uses of other rules before you or after you. You always make a local decision because it's hierarchical and see how far it can take you. It can take you here, but it won't give you that. Okay? It's a good thing to know that there's a limit to all these things because if everything goes, then that's not much of a theory. So next week I'm going to show you how we can turn these, we can take these kinds of ideas and begin to look at them from a computational perspective. Rather than worrying about description and drawing trees, but never caring about how we connect these trees in the first place, we're going to see how we can do that by turning a grammar into an algorithm. Okay? So I'm going to do that next week. All right? So see you next week and stay safe.